Installing a fire hydrant system is a critical aspect of fire protection infrastructure in any urban, industrial, or commercial setting. This process involves far more than simply placing a hydrant on the roadside. It requires a strategic combination of engineering design, hydraulic calculations, adherence to standards, material selection, and construction practices to ensure that the hydrants perform reliably during emergencies. The installation process, when done properly, provides first responders with fast access to high-flow water sources that can make the difference between saving and losing lives and property. This guide walks through the technical and procedural considerations for fire hydrant system installation, suitable for engineers, contractors, developers, and anyone involved in fire protection planning. At the outset of any hydrant system installation project, the first step is site assessment and design planning. This includes evaluating the layout of the premises, building footprints, street access, and existing water infrastructure. Engineers must calculate the required fire flow, the volume of water needed per minute to effectively combat a fire at a given property. This depends on the building's size, construction type, occupancy, and hazard classification. Guidelines from authorities like the National Fire Protection Association, NFPA 24 and 291, or local codes like NBC in Nepal or IS standards in India, are used to determine the required number of hydrants, their spacing, and flow capacity. Once the fire demand is known, the design proceeds to hydrant placement. Typically, hydrants should be placed at 90 to 120 meter intervals in commercial or industrial zones and within 30 meters of building entrances or critical infrastructure. They must be accessible to fire trucks, not obstructed by parked vehicles or landscaping. Hydrants are usually installed along roadways, but in campus-style layouts or large complexes, they may be positioned along internal fire lanes or dedicated hydrant lines. Local terrain, elevation, and accessibility in all seasons must also be considered. There are two major hydrant configurations: wet barrel hydrants, common in warm climates, and dry barrel hydrants, suitable for freezing environments. In wet barrels, water remains pressurized in the hydrant at all times, while in dry barrels, the valve is located below the frost line, and the hydrant only fills when activated. Each configuration has unique installation requirements. For example, dry barrel hydrants need a proper drainage field of gravel below the barrel to allow water to drain and avoid freezing damage. In either case, the hydrant must be set at the correct height, with the outlets 18 inches (45 centimeters) above ground, ensuring easy hose connection and wrench operation. The fire hydrant connects to an underground piping network, usually made of ductile iron, DI, PVC, or HDPE pipes, depending on pressure ratings and corrosion conditions. These pipes are laid from the municipal main or a dedicated fire water tank/pump system. The connection typically includes a mechanical T or anchor T, a gate valve, and a riser. The gate valve, often housed in a valve box, allows isolation of the hydrant for maintenance or repair. Thrust blocks, made from concrete, are installed at every change in direction, T, or hydrant base to resist the reaction forces of pressurized water. Another critical aspect is pipe sizing and hydraulic calculation. NFPA requires a hydrant to deliver a minimum of 250 to 1,000 gallons per minute, GPM, depending on the occupancy and risk. The pipe diameter, usually between 150 mm to 250 mm, is selected to ensure that even the most remote hydrant in the system meets flow and pressure requirements. Hydraulic calculations must account for pressure loss due to friction, elevation difference, and the number of fittings. These calculations are often performed using specialized software or spreadsheets that factor in the Hazen-Williams equation. A fire hydrant system is often supported by fire pumps and storage tanks, especially in industrial or remote installations where municipal supply is unavailable or unreliable. A dedicated hydrant pump room is designed with jockey pumps, for pressure maintenance, main electric pumps, for firefighting duty, and diesel backup pumps, for power failure scenarios. Each component must be tested and commissioned according to the manufacturer's recommendations and relevant standards. The connection from the pump discharge to the hydrant network should include backflow preventers, pressure relief valves, and test headers. Before installation begins, permits and approvals must be obtained from local fire authorities, municipal water boards, and building regulators. The design drawings must be reviewed for compliance with codes. Once approved, the trenching and pipe-laying operations can begin. Pipes are laid on a compacted sand or gravel bed to prevent damage, with proper alignment and slope. Joints are made using mechanical couplings, solvent welds, or flange connections, depending on material. All joints must be pressure tested before backfilling. Once the hydrants are installed and connected, the system undergoes hydrostatic testing, typically at 1.5 times the working pressure for a duration of 2 hours. This is followed by flow testing, where one hydrant is opened fully while pressure is measured at a nearby hydrant. This confirms the flow capacity and pressure integrity of the system. Flushing is performed to clear any debris, and chlorination may be applied if potable water contamination is a concern. Finally, the hydrant barrels are lubricated, caps are tightened, and the hydrants are painted according to the color coding scheme denoting their flow capacity. Signage and marking are an often overlooked but crucial part of the installation. Hydrants should be painted in reflective or bright colors, typically red, yellow, or chrome green. Outlet caps may be color-coded, red for less than 500 GPM, blue for greater than 1,500 GPM, per NFPA 291. Reflective markers, ground pucks, or posts should be installed in areas with low visibility, snow cover, or night operations. The location of each hydrant is then recorded in as-built drawings and GIS systems, allowing fire departments to quickly locate them during emergencies. Post-installation, hydrant systems must be integrated into fire emergency plans, ensuring that staff or residents know where hydrants are located, how they are operated, and how to report issues. Routine inspection and maintenance schedules must be established, usually biannually, where hydrants are operated, checked for leaks, lubricated, and painted. Valves are exercised to prevent seizing, and drainage is verified. Maintenance logs are often digitized, ensuring historical data is preserved and performance trends are monitored. Challenges during installation can include underground utility conflicts, rock excavation, water table issues, or dealing with existing infrastructure. These require coordination with civil engineers, utility providers, and often traffic or road authorities. Safety during construction is also paramount, as excavation and pressurized systems pose risks. Barriers, PPE, confined space permits, and lockout-tagout, LOTO, protocols must be in place. From a cost perspective, fire hydrant system installation is a capital-intensive project but one that pays long-term dividends in life safety, insurance benefits, and legal compliance. The cost includes design, permits, materials, excavation, valves, hydrants, testing, and commissioning. Government and private developers alike must treat hydrant systems not as afterthoughts but as core infrastructure equal in importance to power and drainage systems. In conclusion, the installation of fire hydrant systems is a multidisciplinary engineering task that plays a crucial role in ensuring fire preparedness. From conceptual design to commissioning, every stage must be executed with precision, guided by internationally recognized codes and local regulations. Proper installation ensures that when a fire occurs, the hydrant delivers, literally, under pressure. As cities grow and risks evolve, so too must our approach to hydrant system design, installation, and maintenance, ensuring this frontline firefighting tool continues to save lives for generations to come.